Alright, so for this one, looks like we've got a collision and some kind of sliding with friction. So I guess I'll start with the collision between these two things, right? So we've got M1 and M2. And M1 is this puck that is moving with an initial speed, v1i, of 22 meters per second in the plus x direction, so that direction will be positive. And has an elastic collision with a mass M2 here. And I guess we're assuming that M2 is at rest. Alright. So that's the initial thing anyway. So, okay, so that means since it's an elastic collision, we're told that the block slides 55 meters before coming to rest. So we're really only interested in the velocity v2f coming out of the collision. We really don't care what happens to the M1, to the puck after the collision. So our expression for v2f is that, and then plus blah 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 times 0, because v2i is 0. Now, we're not given either mass, but we are told that M1, if M1 is m, then M2 is 2m. We're told that M2 is twice as massive as M1. So if you wanted to, for example, say that M1 is equal to 1 kilogram, and M2 is equal to 2 kilograms, then that would work. I prefer leaving it as just m, but it really is up to you. So that means this simplifies to 2m over m plus 2m times v1i. So that's 2/3 of 22. So 14.67. That's the final velocity after the collision of m2, which is the initial velocity for part 2. So part 2 involves, it says the block slides 55 meters before coming to rest. Now this part involves motion with constant acceleration, so you could either do work energy or force. Let's draw a diagram. So here's our mass, m2, and it has an initial velocity v0 of 14.67. And it moves across the floor for a delta s of 55 meters before coming to rest, so the final velocity is 0. Okay, our sign convention remains that is positive. Alright, so whether we're going to do this with forces or work energy, we have to identify the forces that are present. So there's normal force, there's gravity, and then there's the force of kinetic friction as it slides, because it's sliding across a rough surface. There's no applied force, there's no tension, there's no spring force, there's no centrifugal force. So we're done analyzing the forces. So let's start with the forces method. Okay, so if I want to use the forces method to find the coefficient of kinetic friction, then I would say, well, the sum of all my x forces is equal to minus the force of kinetic friction, and that's equal to the mass times the acceleration. And the sum of all y forces is equal to plus the normal force minus gravity, and that's equal to 0. So I've got two equations and two unknowns. Oh no, actually wait, I got 3 unknowns, because I don't know mu sub k. Right, I don't know the acceleration either. So what should I do? If you don't know, you should pause the video and think about it before I reveal the surprise. Okay, well, it's not much of a surprise, but if I want to find the acceleration for this part 2 here, I've got enough information to do that. Okay, so if I want to find the acceleration, then I would just use the equation that doesn't have t in it, and that is v squared is v0 squared plus 2a delta s. So 0 is equal to 14.67 squared plus 2 times a times 55. And if I calculate, I get an acceleration of negative 1.956 meters per second squared. It's got to be negative, right, because it points to the left. It slows down, right? Positive velocity, negative acceleration. The mass is slowing down. So, all right, so I can plunk that in right there. I can also, I know that Fn is equal to mg from equation 2, so I can plunk mg in here. After making those two substitutions, the first equation becomes minus mu sub k times mg is equal to ma, and the m goes away, and so mu sub k is equal to minus a over g. So that's minus negative 1.956 over 9.8, which is 0.2. The sign works out to be positive, right? Because you have two minuses. Remember, g is just 9.8. It's just 9.8. The acceleration is negative 1.956, so it works out to be 0.2. Let's do it with work energy method. So for the work energy method, what you do is you calculate the work done by all the forces present in the problem. And the normal force does no work, it's perpendicular to the motion. Gravity does no work, it's perpendicular to the motion in this case. And then kinetic friction, well, the force of kinetic friction is mu sub k times the normal force. You have to multiply the force times the displacement and then multiply by cosine 180. Right, it's the magnitude of the force times the magnitude of the displacement times cosine 180. So this simplifies to minus mu sub k mg delta s. Remember that the normal force is mg. We got that from above. Okay, so the work energy theorem tells me that I add up the works done by all the forces. And I set it equal to the change in kinetic energy. Now we're told that the final velocity is 0 after it slides. Yeah. So I'm left with minus mu sub k mg delta s is equal to minus 1/2 m v naught squared. The mass, m2 here, goes away. And I'm left with mu sub k is equal to v naught squared over 2g delta s, which if you calculate it out is also 0.2.